I'm going to try to teach you new ways that you can solve problems outside the specification. It's not going to be too difficult, I promise, but it's just going to be a new way of thinking about questions. And what this session is not about is not me reteaching you every single reaction from the AS specification, okay? I do have to say, this session I'm only going to be covering reactions that are from AS. So those that are in A2, you have electrophilic aromatic substitution. I won't be covering that, but the questions here will be taken from A2 papers as well, so that'll be suitable for both AS and A2. I won't be going over concepts like Markovnikov's, carbocation stability, electrophilic addition, like the mechanisms, but yeah, I'll just be going over, I'm just going to jump straight in, but we'll just go through the reactions as we go on, so it won't be too difficult. And at the end of the session, you should be able to solve more complicated questions. I recognize that some people really hate the MCQs on isomerism and stuff, but by the end of the session, you should be more comfortable with that, and you should be able to have a go at my question that I've created at the end of the session. But yeah, that's a briefing. I'm just going to show you the question as a document I've sent, but I'll send a link again at the end of the session after we finish. I also have the mark scheme prepared next to me, just in case I make a mistake, so you know what is going on. I'm just going to stream my screen, and that's going to be my whiteboard. So just tell me if you can see it. Can you see the screen? You should be able to. Good. All right. You can see I've just prepared a bunch of questions. These are like the longer response questions, and I've prepared a bunch of paper one, multiple choice as well, because I know people hate like the isomerism questions, so I've just done a couple of that. I would actually like to start off with the final question. Okay, I'd like to start off with the final question, and the reason is, some of you might have seen this, some of you might not. It's called the Diels-Alder reaction, and in this particular question, you're being asked to predict the mechanism without knowing this reaction beforehand, because as you can see, I would assume 99.9% of you haven't seen this reaction before. It's called a pericyclic reaction. You study this at university, but it's asking you to draw 3 curly arrows from this figure to form the final product. So how do you react beta-1,3-diene and ethene to form cyclohexene? Now, I'll give you some thinking space to have a go, but this question is really like the end, is pushing you the end limits of what mechanisms can do at AS level, but it's really about following the pattern. So does anyone have an idea? Has anyone seen this question before, importantly? Because I don't know where I got this question from. I just remember someone sending it and I just copied it here because I thought it would be interesting. It's quite a distinctive question, I'd say. Yeah, Mayonnaise sent it. That's why I copied it. I remember this. Yep. So now if you look at this question, I'm going to try to explain it in an easy way. What I recommend people doing, if they don't know what is going on in a question, in an organic chemistry question, especially when you have like loads of skeletal formula, is labeling the carbons, okay? So what I would do first, if I see a question like this, I would label the carbons with numbers. So you can see here, I'm going to call this carbon number 1, and I'm going to go anti-clockwise. So I'm going to call this 2, call this 3, I'm going to call this 4, okay? On this side, I have 2 carbons, so I'm going to call this, let's just call this A and let's call this B, okay? So you can see we have 6 carbons in total, and from the final product, you can see there is a cyclohexene, so that's 6 carbons as well. So what I'm going to do is I'm going to follow the pattern, okay? I'm going to follow the pattern. And you can see here, this kind of resembles a first carbon. So 1, 2, 3, 4, and you can see carbon 4 has joined up with carbon A, and carbon 1 has joined up with carbon B. I'm going to label this A and B, okay? And now you just have to draw the mechanism of this, all right? So it looks complicated because it is. It's a really difficult question for AS, but just follow the pattern, okay? you can see we need to form a new bond between carbon 4 and carbon A, right? And we need to form a new bond between carbon 1 and carbon B. And the way we're going to show it with the mechanism is we need to push electrons between carbon 1 and carbon B, right? So the electrons from, let's just say we move this double bond. Let's focus on this double bond for now. There's 2 electrons in this double bond, right? We know to form a new bond between 1 and B, we need to push these 2 electrons between 1 and B. Okay, so the way I'm going to do this is I'm going to just keep the 2 electrons here for now. I'm going to push the arrow towards this carbon, okay? Push the arrows towards this carbon. So the electrons from carbon 1 are going to be transferred between carbon 1 and carbon B. So I form a new bond there. And what's the problem with that? If you take 2 electrons away here, right, and you form a new bond between carbon 1 and B, then carbon 2 would be electron deficient because you've taken away 2 electrons from it. And you can draw in the hydrogens as well if that helps. So if I draw in 2 hydrogens here, so if I form a new bond between carbon 1 and B, then carbon 1 would have 4 bonds because I'd erase this bond, I have 4 bonds. But carbon B, on the other hand, would only have 3 bonds because if you take away this bond, you only have 3 bonds. So you would want carbon 2, I said carbon B, I don't know why I said carbon B, but you want carbon number 2 to have 4 bonds. So it's all about following the pattern, like labeling your carbons, and then you want to figure out how to get everything to 4 bonds as well, okay? So the way this is going to work, I push this double bond over here, and this double bond, the 2 electrons here, are going to fall down into here, okay? They're going to fall down there. And the reason why is because carbon number 2, as I said, if you push electrons away from 1, it's going to become electron efficient. So you're going to push electrons down back to carbon, between carbon number 2 and 3, to make it like electron, you just give it back the electrons basically. And that makes sense because if you look at the final product here, it's about following the product as well. Is if I take this double bond and just push it over here, the double bond's going to be between carbon 2 and 3, right? That makes sense because in the final product we have a double bond between 2 and 3. So we're just going to put it down here. And the final step of the mechanism is if you push electrons away from carbon number 4, right? If you take your electrons away from carbon number 4 and push it between 2 and 3, like here, then carbon number 4 would be electron deficient, right? So you just go ahead and take the 2 electrons here from this double bond and just push it over here. And that would give you your Diels-Alder reaction. You can see it's kind of like in a clockwise pattern of pushing arrows, but that's the only mechanism that is allowed to get to this product. And I should probably mention, you would be allowed to put the arrows in an anti-clockwise direction as well. So my first arrow I've drawn here is this way, but it's also okay to draw it this way. Then you would just push it in the opposite direction. It's kind of like a cycle. You just do a cycle, and yeah, that's how you predict this mechanism. Does anyone not understand what is going on? Because I'd imagine this is quite a difficult concept to wrap your head around. The last part, what about the last part? Can you specify? Like as in how I said you can push in either anti-clockwise or clockwise direction. You basically have to make sure that all of them are 4 bonds, okay? If it helps you, you can draw them in this blade formula. Some people don't like skeletal formula, so you can draw them in this blade formula if you want. So this is butadiene, right? I'm just drawing the hydrogens here, and I'm going to draw ethylene on the right. So this is basically that in this blade formula. You can see if this double bond breaks and forms a new bond, because we need to form, I'm just going to number the carbons in a different color. So 1, 2, 3, 4, and then we have A and B. We know carbon number 1 has to join to carbon number B, right? So we're saying that we push this arrow to join a new bond. So if we push this arrow down there, then we're taking away this double bond and we're forming a new bond like this, right? And the problem with this is if you look at this carbon here, that now has 3 bonds. So 1, 2, and 3. That's not good. Carbon always likes to have 4 bonds. So we're going to go ahead and just push this double bond down here. So it's not electron deficient anymore. So I'm going to take away this double bond, right? Push it down here. So now this has a double bond. And the reason why I push it down here, because you can look at the product, right? Between carbon number 2 and 3, there's a double bond. Between carbon number 2 and 3, there's a double bond. So you push it down there, you follow the pattern. And then now look at carbon number 4. Carbon number 4 now has 3 bonds. That's not good either. So you have to push this down here. And you can see from the product, you need to join up carbon number A and carbon number 4, right? Carbon A and carbon 4. And by pushing this double bond down here, you're forming a new bond between carbon number A and carbon number 4. So that looks messy, but in skeletal formula, that's just cyclohexene. Okay, does that make more sense? It's quite a difficult, it's obviously a difficult question, and I doubt that you get something similar. I really doubt that. But this is just, again, stretching your brain, really, thinking about chemistry in a new way. The next one is kind of a similar question. You're still using Diels-Alder to do something. So Diels-Alder reaction. And again, it's about following a pattern. It's asking you to predict the product. So you're given the reactants and the products in the first part of the question. So you should be able to predict what's going to happen in the last part of the question, okay? Again, if you follow the pattern, it's going to be really easy. So when you don't know what you're doing with an organic reaction, you always number them, right? So I'm going to number them 1, 2, 3, 4, as usual. And this side, I'm going to number them A and B. I can even use 5 and 6 if that's less confusing. So I'm just number them in an anti-clockwise way. So from this reaction scheme up here, if I number this as well, like I have, then you can see that in the final product, we kind of have a complete ring of carbon 1 to 6, okay? So carbon 1 to 6 is joined, carbon 4 to 5 is joined, all right? And you can see the double bond, the only double bond left, I have 3 double bonds starting with, but the only double bond left in the product is between 2 and 3, all right? So I know this is going to join up to a ring. These 6 carbons are going to join up to a ring, so why not just draw a ring, okay? Just draw a 6-membered ring and renumber them 1 to 6. Like this, and then I can see that a new double bond is going to be between 2 and 3, right? So I'm going to draw a new double bond between 2 and 3. That's exactly what's going to happen, by the way. And we can see we have this part of the molecule that we have to draw as well. Don't be scared because it's a ring. It's just going to be a molecule of 2 rings. So on carbon number 5, I kind of have this structure, right? On carbon number 5 and 6, so carbon number 5 is bonded to like this structure. And you can see that is the final product of that reaction. So again, I just number the carbons, I follow the pattern on the top, I see the double bonds between 2 and 3. That's the only double bond left, so I just draw it between 2 and 3. And then the rest is just adding in what's left. Does that make sense? Does that not make sense to anyone? What happens to double bond at 5 and 6? Oh, can you see? It's hard to visualize, but the double bond here, 5 and 6, as I said, in a mechanism, you move the electrons from 5 and 6, and then you do it like this, right? So the electrons here have moved to form a new bond between 1 and 6. That's what's happened, okay? That's why you only have 2 and 3 remaining, because when you push this down, you have to put it in the middle. That's just a mechanism of the Diels-Alder reaction. Does that make sense? Okay, I'm going to assume that makes sense because I don't get any other inquiries. There's going to be time at the end of the session where you guys can request a question, and I'll just re-explain any concepts that are not made clear in the first place as well. And yeah, so that's a really unfamiliar reaction, but that's how I would predict a mechanism and how you should as well. So number the carbons and just follow the pattern. And speaking of unfamiliar reactions, we're going to go ahead and do this question using, it's called the Wittig reaction, which converts an aldehyde or a ketone, like carbonyl group, the CO group, into an alkene. But the first part of the question is fairly straightforward. Give the empirical formula of triphenylphosphine, which is this thing here. So we can just go ahead and count, really. But you can see here, one of these phenyl groups is C6H5, and we have 3 of these phenyl groups here. So that's just going to be 3 times C6H5, which is going to give me C18. and H15, right? And you can see in the middle we have a phosphorus atom, and that's P. There's no way to simplify this ratio into a simpler form, so it's just going to be, this is the empirical formula. Order does not matter. You can put it like P first, or H first, or C first. It really doesn't matter. You still get the mark. That should be a fairly straightforward part of the question. The next part of the question is where you apply, again, an unfamiliar reaction to what's actually happening. So in a Wittig reaction, the aldehyde here reacts with the halogenoalkane to form the alkene. And you can see what's going on here. So what really is going on, again, you can see the oxygen is being taken away, and you form a new alkene with a carbon. This is a new carbon, right? There isn't a carbon here, but you've added a carbon in that's attached to the R group. So what's really happening, if I draw this, taking away this, borohydride, aldehyde plus sodium borohydride, that should be a common reaction. What do you think that forms? Yeah, this is CIAE chemistry, not another specification. It is reduction. So you would reduce the aldehyde into an alcohol, right? You reduce the aldehyde in alcohol. Specifically, if you really wanted to, you would get, well, this is kind of wrong. You would get, always like, these formulas sometimes confuse me, so I always like to draw stuff out. You can do it in displayed or skeletal, it really doesn't matter. You get propanol, propanol. So stage 1 is reduction with sodium borohydride. Stage 2, okay? So we get G, which is this alcohol. We react with it with red phosphorus and I2. So what's happening is our iodine is, well, we can call it iodide. Iodide is substituting this alcohol in some sort of way, right? So you can see, if I draw this out, it's going to look like this. This OH group and this group has swapped, okay? If something is swapped, if the functional groups have swapped, then it's just going to be substitution. You just call it a substitution reaction. I don't know if you've seen the red phosphorus and I2 reagent before, but using that logic, the groups have swapped. It's just a substitution reaction, okay? Draw the structures of G and H. That's why I like to draw stuff out like this, because we already worked out G. It's just going to be propan-1-ol, because the reduction of propanol. H is going to be a Wittig reaction, okay? So you can see here, stage 3, they've labeled Wittig reaction. So we can draw this out. We already have drawn this out, and we can draw this out as well. I'm going to draw it out like this time. So that's propanol. And you can see, you're given the scheme of the Wittig reaction here on the top, right? You're given this haloalkane. So if I draw it out in this orientation, that's the same as this, right? That's the same as that. I've just drawn it out like this because it's easier to see this way. So you can see that this is our R group, this is the R group, and this is the iodine, okay? So the carbon is gonna replace the oxygen and form a double bond to this carbon that was used to be bearing the oxygen, right? So if I draw them together, if I draw the reagents together, so let me just take this here, and if I take this haloalkane that we have, that's from this and that's from that. So if we join them up together, from the scheme above, you can see that we would get rid of the oxygen, right? The oxygen, there's no oxygen in the final product. We get rid of the iodine, there's no iodine in the final product. And let me just remind you that this is not a carbon, okay? So we have 3 carbons here, and we have this double bond. And what we have to do is we just join them up together. And that is your final answer. That's it. Okay, so let me just repeat what's happened. I had this propanol and I had this haloalkane, right? When I react them together, this part is going to go away, and I'm going to connect this carbon to this carbon here. So like this, you form an alkene. You replace the aldehyde with an alkene, with the R group on top of the alkene, like that. Does that make sense or does it not make sense? If something doesn't make sense, you just got to tell me. I'll help you as much as I can. Makes sense? It's all about following the pattern. You've never seen this in your life. 99.9% of you would have never seen this in your life. But once you follow the pattern, it's really quite simple. Okay. You can even number the carbons if you really wanted to. Well, for example, you can call this carbon A, and you can call this carbon B, right? You can see here carbon A and carbon B have joined up with a double bond, and then the R group is just this propyl group we have. That's pretty much it. Yes, the session is going to get recorded. All right. So the structure of H I've worked out is just going to be like this. Importantly, though, there's no EZ isomerism in this that you are required to know. Okay, you don't need to. You can draw either E or Z isomer. So, for example, I've drawn in the E isomer here, or trans isomer, because these two ethyl groups are on different sides. But even if you drawn in this, where both ethyl groups are on the same side of the alkene, you'd still get the mark. Okay, doesn't really matter. All right, we can move on. Identify the organic product formed when compound J, shown below, is heated with hot concentrated acidified manganate ions. So you should know that hot concentrated manganate ions, so potassium manganate, for example, would lead to oxidative cleavage of the alkene to form two carbonyl groups. So there's a difference between hot and cold. So for example, if I had let's say I have this alkene here, like butene. If I did it hot with MnO4, I would split this bond apart. I'm going to use a different color. I would split this apart, and I would just replace them with a carbonyl group. And this is going to become a carboxylic acid because we basically just add an OH, extra OH there. So I would get two carboxylic acids, two acetic acids if it was hot, okay? If it was cold, it wouldn't be oxidative cleavage. It would be a dihydroxylation. So you would just break this double bond and accept two OH groups like this. Okay, that's the difference between hot and cold. Hot, it's hot enough so you can cut a bond. If it's cold, you don't have enough energy to cut the bond, so you just add two OH groups to there. Okay, kind of included a diagram here. That's including the mechanism. You don't need to know the mechanism, okay? Let me assure you, you do not have to know this, but you can see here how it is just cut open. The bond is cut open, and then you've got two aldehydes, which because of the presence of more manganate ions in the mix, will get oxidized to a carboxylic acid. Okay, because when you cut it, you form an aldehyde, but it will get oxidized further to a carboxylic acid because you have more oxidizing agent, which is the manganate ions in the solution, right? So is that similar to ozone analysis? You had me think about what ozone analysis is. Yes, that is similar to ozone analysis, but for people who don't know ozone analysis, don't worry, but ozone analysis is basically like getting an alkene, doing O3, and then like a reducing agent, and then you just split it into two carbonyls. That is kind of similar, okay? The only difference is you don't oxidize it further in that reaction. But anyways, that's out of the specification. We can do this reaction then. So hot concentrated, again, we just split the bonds. You can number the carbons again if you want. So 1, 2, 3 on this side. I'm going to call this A, B, and C, okay? So 1, 2, 3. And you can see on the third carbon, I'm going to replace it with a carbonyl group, right? And then I'm going to add in, it's basically going to be an aldehyde, but because it's going to get oxidized further, I'm going to add OH. So aldehyde oxidized to a carboxylic acid, okay? For this part, I have carbons A, B, and C, right? You can see on carbon B, I'm going to replace it with an oxygen group. And now a ketone cannot be oxidized further because it's secondary. It's okay. It's a ketone. It can't be oxidized to a carboxylic acid. Only aldehydes can. Make sense? Can you repeat the hot and cold part? So the hot manganate ions would make you split the double bond in half and replace it with carbonyl groups like this. Okay. So you can see here, this part resembles this, and this part resembles that. Okay. You would form a carbonyl group that would be an aldehyde at first, but because, so if I draw the aldehyde, it would be like this, wouldn't it? Right? But because of the presence of more oxidizing agent in the solution, so more manganate ions, it would get oxidized to the carboxylic acid. So you replace the H with the OH because aldehydes get oxidized into carboxylic acids. Okay. All of these questions, I believe, are taken from an A2 paper, a proper paper. So all of these questions here, long response, but only the small ones, the MCQ, are taken from paper 1, which is AS. Okay, we'll do the MCQs later. Does that question make sense to people? Does it not make sense? Does any part of it not make sense? Okay, it does make sense. Good. Right, we can move on. Well, I don't know why I'm not doing this in order, but that works. We can do the first question now. Okay, so this is just like some context. You always get some context at the start of the question, and then you get a bunch of information that you have to answer. Right, so the question is, M reacts with hot concentrated acidified potassium manganate. So again, you should know what that does. It just splits the double bond to form N. It gives you the molecular formula as well in reaction 1. Draw the structure of N. Right, you're given this reaction as well, where you can see here, this is an intermolecular esterification. That word scares a lot of people, okay? And all I mean by that is it's esterification because you got a carboxylic acid and an alcohol in the same molecule, right? It looks scary because you have never seen this before, maybe. But if you remember esterification, even from IGCSE, it's a condensation reaction, so you remove water. So if I highlight H2O here, right, and I just cross it out, and you can see here, this oxygen would be joined up to this carbon, right? We can also number stuff again. Always like numbering stuff. 1, 2, 3, 4, 5, right? And this oxygen, number 5, is going to be joined up to number 1. And you can see that in the product, 1, 2, 3, 4, 5. This oxygen on number 5 is joined up to the carbon, bearing this CO group in number 1. Okay? That's all this reaction is about, is intermolecular esterification. All right? And, okay, this question is asking what happens when you react with potassium manganate to form N. So you want to work out N, okay? I can see 2 ways of working out this question, and one way is significantly harder than the other. All right. The first way you can do it, which is the really hard way, is by splitting this double bond and then drawing out the product. So I'm going to show you how to do that again. Because it's difficult to visualize, I'm going to number my carbons like this, okay? I'm going to number this methyl group number 6 as well. So if I split this apart, I'm going to open apart the 6-membered chain. So I'm going to draw a 6-carbon skeleton here. So 1, 2, 3, 4, 5, 6, right? I can see on carbon number 1 is where I've broken the double bond. So I'm going to have a CO bond here. That's going to get oxidized further to the carboxylic acid, okay? And I can see on carbon number 5, that's going to get oxidized. I mean, that's going to get oxidized. So on carbon number 5, where I bare the double bond before, I'm going to have a carbonyl group as well. And that cannot get further oxidized into a carboxylic acid because it's a ketone. Right? Does that make sense? That's another way to think about questions like this. Okay. Draw the structure of N. I'll just draw it out. Right. N is reduced by sodium borohydride to form 5-hydroxy hexanoic acid in reaction 2. So we know what happened here. Construct an equation for equation 2 using molecular formulae. In the equation, use H to represent one atom of hydrogen atom from the reducing agent. So this is just about writing the equation using the reducing agent, right? It's writing the equation using the reducing agent. So, of course, you would need to work out the molecular formula of this, wouldn't you? So, might as well do it. So we know there's 6 carbons, because it's hex, but then the hydrogens is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 hydrogens. Oh, there's one here. I didn't miss that one. H10. So oxygen should be easy. It's just 1, 2, 3. So that's the molecular formula, right, of N. And then you can either work this out or you can just know it, okay? You can see from a ketone, if I just focus on a part of a ketone, let's ignore the sides. I'm going to use squiggly lines to omit the sides. You can see from a ketone to an alcohol, right? Remember this carbon, on this carbon you have a hydrogen because it needs 4 bonds. You can see that it's gained 2 hydrogens overall, right? So that's one way to think about it, or you can just memorize it and know that from ketone to the alcohol you gain 2 hydrides or hydrogens, and then you reduce it to this, which is now you gain 2 hydrogens, right? So that's just H10 plus 2, which is 12. Does that make sense? Only cool nerd is saying yes. Slightly concerned for like the 40 other people. Okay. Great. That should be standard though. It shouldn't be too difficult. Can I say again, please? Which part do you want me to say again? The reaction. Okay. So you're using sodium borohydride. If you look over here, using sodium borohydride to reduce the ketone into an alcohol, right? You can see here, if I turn a ketone into an alcohol, then I gain 2 hydrogens. 1 hydrogen for the carbon, because the carbon needs 4 bonds, right? Because you lose a double bond, the CO double bond, and you need to form a new bond to have 4 bonds. So you gain 1 hydrogen, and the alcohol, because you gain going from O to OH, you also gain another hydrogen. So the way to represent this is the molecular formula of N. You add 2 hydrogens to give you this, which is just this molecular formula plus 2 hydrogens to give you from H10 to H12. Does that make sense? Okay, cool. Right, reaction 2 is a nucleophilic addition. Suggest why reaction 2 creates a mixture of 2 compounds. So this is a really like stereotypical question, really. So reaction 2, we're going from the ketone, again, I'm going to use squiggly lines to just omit the sides, and you're using NaBH4 to form the alcohol, right? And you can see that this is a chiral center, okay? Specifically here is a chiral center because you have 4 different groups on the same carbon. It's a chiral center. So you can have a mixture of enantiomers, 2 enantiomers. So 2 stereoisomers from that. And the reason why is there's a general rule in chemistry. If you start with 2 achiral, so not chiral substances, you can clearly tell that NaBH4 is not chiral, right? NaBH4 is this. And you can tell the ketone that we have, it's planar, it's trigonal planar. It's also not chiral. It's only got 3 groups on it. A carbon can only be chiral if it's tetrahedral. Okay, you can see we have 2 achiral starting materials. A general rule is if you have 2 achiral starting materials that react, you'll never get something chiral. You will also get, you will get a, oh dear, you will get a chiral product. Okay, you can see this carbon now becomes tetrahedral. And the reason why is you can think of the ketone as a flat surface. I'm drawing the ketone as in it's like in a plane of paper here, right? You can see the ketone. Now, I'm going to draw out the borohydride like this. the nucleophile, you don't need to know this, but I'm just showing you for purposes. The nucleophile in this reaction is the BH bond. It's nucleophilic. The electron in this bond will either go from the top, right? You can see there's an orbital here. It would either go from the top of the orbital, or it can go from the bottom of the orbital if I have a BH4 on the bottom. This is not in the specification, but it's just good for illustration purposes. You can see it can either go from the top or the bottom. Okay, that's the reason why. So you can either get a product where the H is pointing up and the oxygen is pointing down if you go from the top, but if you go from the bottom, then the H would be pointing down and the oxygen would be pointing up like this, right? So the exact wording you would want to write would just, I'm just checking the mark scheme just to make sure because I'm not very good at mark schemes. It's the ketone is planar, so that's the first point. The ketone is planar, as you can see here. It's on a flat surface, and it can be attacked from either side. That's the first mark, okay? The second mark is different stereoisomers can form. You can see enantiomers and stereoisomers. Because the question is asking you, a mixture of two organic compounds, you need to specify what the mixture is. It's just because of stereoisomers, okay? So it's because it's planar, you can attack from either side. Therefore, you can form two stereoisomers. Does that make sense? Cool nerd saying yes again. Okay, good, great. Glad it makes sense. So if there's no other questions, we can move on to this question, the next one. Any questions? Yep, okay, cool. The next one then. C can be used to form H. Okay, so C is down here, H is up here. One possible synthesis of H is shown in figure 4.5. Different portions of C are used in reactions 1 and 3. So reaction 1 is this, and reaction 3 is this. Some of the products are now then combined to produce H. So J and G. J here, G here. It does not show any of the inorganic products, so only organic products, no side products basically. So we're only looking at the main product. And we have to complete the table of reactions and reagents. Okay. Whenever you get something like this, I always recommend just trying to work out what everything in the question is. Then everything else will become stupidly obvious. All right. So you just have to figure out what's going on. So you can see here, that's just electrophilic addition with the halogen going on a more substituted carbon, so on this carbon, but not this carbon because of Markovnikov. Well, they worked that out for you. And then here's the weird part where they just say, oh, E forms J, and J reacts with G to form this. Okay. So what is J? What is J? Again, you can just follow the pattern really. Like you can look at this structure. You kind of have like this, I'm just going to highlight it. You have this bit here, which looks similar to this bit here, right? And you can probably guess, if you're sharp enough, which I hope you are, you can probably guess that this is an ester. This looks like an ester. It's going to be formed from a carboxylic acid and an alcohol, right? So if we kind of disassemble this, if we break this bond apart, we're going to get this carboxylic acid and this alcohol, right? Is that clear? Like that's an ester, and if you break it apart, you get a carboxylic acid and an alcohol. It's just that. And you can see here, this alcohol somewhat resembles this structure. So J, let's just say J is this. Okay, let's just say J is this alcohol. And so reaction 3, when you form a ketone from an alkene, it's going to be some sort of oxidative cleavage with potassium permanganate. Because again, if we split this bond apart, we can number the carbons 1 through 3. So for the first one, we would get a ketone here, right? And for this part of the molecule, so I'm going to label it A and B, I'm going to get a new carbonyl group from the carbon that was bearing the the alkene. So I'm going to get a new carbonyl group. This is going to be an aldehyde, but it's going to get oxidized further into a carboxylic acid. Okay, does that make sense how I split this into these two products here? That should be a familiar skill by now, right? And you can see here, one of the products indeed is propanone, our propanone here. So the other product, G, must be this thing, which is acetic acid or ethanoic acid, okay? And now that makes sense because you can see when G reacts with J here, G is this, right? This is G and this is J. That forms H. So it is esterification overall, okay? So let's just summarize my thought process. The first thing I thought when I saw this question was it's an ester. So it must be formed from an alcohol and a carboxylic acid, right? So I must have a carboxylic acid and an alcohol in J and G, and that's how I got it. I just followed the pattern. Okay, great. And now you just have to identify the reagent and conditions. You don't even need to identify J and G themselves. You just have to identify the reagents and conditions. But you definitely have to work out what the identity of J and G is before you work out this. Okay. So let's look. From E to J, we substitute Br with OH. Okay. That's nucleophilic substitution. It's SN1, not SN2 because it's a tertiary carbon. So SN1, the conditions, does anyone know what the conditions you would use for this is? What would you use for SN1? Steam. Steam is an interesting choice. I do not believe steam would be a valid answer. It would be aqueous NaOH, indeed, yes. So the difference between aqueous and ethanolic, hopefully you know. So when do we use aqueous NaOH and when do we use ethanolic NaOH, which I'm going to abbreviate as F. So this is for sub and this is for elimination. The reason why is if you want substitution, you want more OH minus ions to kind of substitute that in, right? To substitute this carbon. And in aqueous, you have H2O, which effectively gives you a source of OH ions, right? Whereas in elimination, you want to make sure that substitution doesn't happen. Okay, because let's say I have something like this, right? Let's say I have something like this. You wouldn't want the OH ions to attack this and substitute. You want to do an elimination where you form a double bond there, right? In that case, you want to minimize the concentration of OH ions so that they don't attack here. Right, that's the difference. That's why I use ethanolic NaOH for elimination and aqueous for substitution. But yeah, the reagent for this, it's substitution, so it would be NaOH AQ. Or potassium hydroxide, or any hydroxide that you can think of, that's appropriate. Next one is oxidative cleavage of this alkene. So C to G in that. Well, again, if you see an alkene to a carbonyl, that's usually just KMNO4 AQ acidified. So that has H plus ions. So you can write acidic KMNO4. That has to be hot. Okay, you have to write hot because if it was cold, it would be a dihydroxylation. You just add two OH groups. You won't cleave it. And then for some reason, because I looked at this yesterday, you have to write concentrated KMNO4 for oxidative cleavage. Okay, so three conditions: concentrated, acidic, hot. Okay, if it was cold, it would do the different thing. Make sense? Yes, Cambridge. It is Cambridge. It's pretty much the explanation. How cold and hot affect the products? Well, the easy explanation is if it's hot, you break the double bond. You have enough energy to break the bond, right? If it's cold, you don't have enough energy to break the double bond, but what you can do instead is just add two alcohol groups to it on each carbon. So basically just add OH and OH. Okay, that's the difference between hot and cold. Is cold also concentrated? Great question. I'll actually look it up. Because I would not want to just make a call. I do not know these mark schemes. No, you use dilute for cold. I assume because you don't want to oxidize it too much that you just break the double bond. So for cold dilute, hot is concentrated. So basically you can see the difference between hot and cold. Hot is breaking it, cold is just adding to it. Okay. It does matter, I believe. It does matter. There's no way it doesn't matter if it's in the mark scheme. But okay. Anyways, reaction 4 is esterification. So we do J, which is the carboxylic acid, plus G, which is the alcohol. So if it's esterification, you use concentrated H2SO4. And that's not aqueous. It can't be aqueous. Because if you think about it, you're making an ester, right? Ester hydrolysis is when you add water to an ester, break it back into your starting materials. You don't want that to happen because you want to form more of the ester. So usually esterification is done with trace amounts of the concentrated acid as the catalyst under anhydrous conditions. So just liquid form of the acid, not aqueous, because if it was aqueous, the water would hydrolyze the ester back into its constituent parts. You don't want that to happen. Okay. Right. Does anyone have any questions regarding that question? Or is everything okay? Good. Okay. We can move on. Next one's quite a short one. C2 can be synthesized by using A1 as a single organic reactant. Okay. Devise a multi-step synthetic route to form C2 from A1. Identify relevant reagents and conditions and state the organic products of each step. So you're only allowed to use A1 as the starting organic material. Okay. So what I mean by that is you can't just get a propanol and a react with the aldehyde to form this. That's also another type of esterification, by the way. But you can't just do that. You have to use A1 to form C2. I don't know why it's called A1 or C2, but you know. So you can see again, ester. It's an ester. So what do we have from the starting materials? It's probably going to be a carboxylic acid and an alcohol, right? So if we break this bond just to see what's going on, and we add water across it, you can see that C2 is formed from this carboxylic acid, so propanoic acid and propanol, right? Can you see that? And well, you just remove H2O to reform the ester here, but that's the starting materials. So how do we get propanoic acid and propanol from this aldehyde? That's all the question is asking, and it really should be straightforward enough to see that. You can see that from aldehyde to carboxylic acid is oxidation, and from aldehyde to this alcohol is reduction. Okay, so let's look at the oxidation first. To go from this, so to go from propanol to propanoic acid, you would use, there's a range of oxidation agents, but the common one at A level is potassium dichromate. Acidified, okay, so acidified potassium dichromate. You can do it under reflux if you want to, but I think that's enough. Okay. I'm not sure if it writes hot on the mark scheme. I'll just check to make sure because I genuinely have. I don't want to misguide you guys. Yeah, that would be enough just to write acidified potassium dichromate. Could you use potassium manganate? You can use potassium manganate. Yes. You can use potassium manganate. That would be allowed. It has to be acidified. Don't forget the acidified bit. It's crucial. Okay. Yeah. So that's the oxidation reaction. And that is the propanoic acid. So identify the organic products as well. Don't forget. For the reduction, that should be straightforward enough as well. To get from the aldehyde, so propanol to propan-1-ol, you would do reduction with sodium borohydride. Any carbon in reduction to alcohol, just use sodium borohydride. Okay. If you wrote lithium aluminium hydride, that wouldn't be accepted. I always say lithium aluminium hydride is like, it reduces carboxylic acids or amides, I don't know if you've learned that, into alcohols, right, using lithium aluminium hydride. But using lithium aluminium hydride to reduce an aldehyde or a ketone is like using a sledgehammer to kill a fly. It's overkill. It's way too overkill. It's a really vigorous reaction. You wouldn't want that. Okay. So sodium borohydride is kind of like the mild option, the soft option, where lithium aluminium hydride is like the really hard option. Okay. You don't want to do that. Why acidified? It's just because the acids like it's complex because the acids produce I mean not produce, it's like a redox reaction with the potassium dichromate that the acids do in order for the alcohol. I can send you the equation. Like if you look at a full equation for this, which you don't have to know, you can see that acids are a key part of doing the oxidation. It's just part of the equation. So I've sent it in a chat there. You can see it's a really long redox equation, but that's the reason why. Okay. You don't have to know why though, don't worry. Good question. So does anyone have any questions regarding this part of the question? So again, I'll just summarize what I've done. I've seen an ester. Anytime you see an ester, just cut the bonds. Okay, cut the bonds, reform the carboxylic acid and the alcohol, and then I just worked out how to get from the aldehyde into the carboxylic acid by oxidation and to the alcohol by reduction. Does that make sense? Yeah, works similar with manganate. Lithium aluminium hydride, no, it won't be accepted. It works, but it's like hydrogen bomb versus fetus, basically. You won't want to do that. It's way too vigorous. Using a sledgehammer to kill a fly, as all the professors like to say in chemistry. But yeah, I suppose we can move on. Last two questions, and then we should go to the FAQs, which should take way less time. All right. This session is less than 2 hours, so we have an hour left. Some reactions based on 1-bromobutane. Okay. The thing about this is I hate structural formula, so I always try to draw them out if I can, but 1-bromobutane, it really should be easy to draw. So you can see it's like a whole synthesis scheme, and you just have to work out reactions 1 to 6, reagent conditions, and type of reaction. You have to get both columns right to get 1 mark, because it's 1 mark for each 2 columns, for each row correct. Okay, so we can just do our annotations based on this, really. And yeah. Are there no A2 questions? I try to fit this for AS as much as I can, so you won't see stuff like electrophilic aromatic substitution. You won't learn that here. Hopefully the style is suitable for A2 as well though. But anyways, we can just annotate the reactions really. So we can see here, in reaction 1, you go from the bromine to an OH. Nothing else has changed, so it's just substitution. So I'm going to label that sub with OH, which is probably some sort of NaOH aqueous, right? So let's go down this route. Reaction 5, we go from an OH, so an alcohol, to an aldehyde. Nothing else has changed, okay? You can see here the 3 has decreased to a 2, but that's just because, like, I went from butane 1-ol, this carbon here, to this, okay? That's just because the CHO, I'm just taking out the carbon here to write it in the aldehyde CHO, okay? The number of carbons have not decreased. So, well, alcohol to aldehyde, that's just oxidation, so I'm going to write oxidation. And if you want to get from an alcohol to an aldehyde, you want to distill it out, okay? You want to do it by distillation. Because if you don't do it by distillation, if you heat it under reflux where the aldehyde goes back in the reaction mixture, then you would get a carboxylic acid, okay, where you would just get this. So distillation, and this is reflux, okay? If you want to go directly from alcohol to carboxylic acid, you would do reflux with an oxidizing agent like potassium chromate, potassium permanganate, etc. But okay, let's go down again. So reaction 6, and now that's where you get from the aldehyde to the carboxylic acid. So 2 separate reactions you get from the alcohol to the carboxylic acid. So if it's aldehyde to carboxylic acid, well, just oxidation, reflux. Okay, oxidation by reflux. Cool. Right, that's my annotation. So let's go down reaction 3 now. You can see from bromine to this cyanide, we just do a nucleophilic substitution with the cyanide ion. So you should be familiar with the reaction. So the cyanide ion just kicks out the bromine in SN2. Okay, another really boring substitution. So just sub with, well, for example, KCN. Okay, potassium cyanide. And from 4, this is like a bit more niche reaction, I guess. But when you convert a nitrile, so a CN, into a carboxylic acid, as you can see here, that would be hydrolysis, okay? That can either be base catalyzed or acid catalyzed. You can, like, any hydrolysis, any sort of hydrolysis in chemistry, you can either put acid catalyst or base catalyst. It doesn't matter. It does the same job. I'll just read the chat because there's a lot of stuff. If a question is asked what type of reaction 5 is, yeah, reaction 5 is oxidation because you're going from an alcohol to an aldehyde. Reaction 6 is also oxidation because you're going from an aldehyde to a carboxylic acid. Okay, distillation is the process you do in a reaction, not the type of reaction. Okay, distillation is a condition, not a reaction. Can you use HCN for reaction 3? Yes, you can. You can use HCN, which is really perplexing because I remember reading this in a mark scheme that allowed HCN. I found that confusing because using hydrogen cyanide, HCN, in an actual lab would be very dangerous. So, well, you know, in World War II, World War I, I believe it was, not talking about politics, but they used HCN, hydrogen cyanide, as a toxic chemical called Zyklon B, just to kill people, basically. So HCN is really dangerous in a lab. So I don't know why they would allow that, but in a mark scheme, you know, in an exam, on paper, you won't accidentally just kill yourself with HCN. So I guess you can use it, okay? But you can use any sort of cyanide for this reaction. Make sense? Lithium aluminum hydride is not oxidation, it's reduction. Just be careful. Yeah. And again, it's using sledgehammer to kill a fly, so you wouldn't do that to a ketone and an aldehyde. Great. So reaction 4 is just hydrolysis, as I said, H2O. You can use H plus or OH minus. And I believe it's like dilute acid or something. I remember in the mark scheme. I don't know why it's dilute. I have no clue why. You just have to know it. I'm going to check just to make sure. Reaction 4 is dilute. Oh yeah, dilute. Like for example, dilute H2SO4 or dilute NaOH as a catalyst. Okay. Right. So the last thing we're missing is reaction 2. That's converting a haloalkane into an alkene. So that's elimination. So you go from this, sorry about the messiness, to butanene. Okay, so that's going to be elimination. And with elimination, you would use any sort of hydroxide or base, but that would be ethanolic. Okay, it won't be aqueous for the reasons I've explained before. Has to be in ethanol. Okay, if it's aqueous, it would do substitution, which is what not you want. Make sense? Does anyone have any questions for these reactions here? How do we know when just to do heat and heat under reflux? So when you do distillation, okay, you can see here, when you do heat under distillation, you stop the oxidation at an aldehyde. So to go from alcohol to aldehyde, you do distillation. because as soon as you get the aldehyde, it will be distilled out as a vapor. You collect it, okay? But when you do reflux, on an alcohol, you directly convert it into a carboxylic acid because the aldehydes would get refluxed back down into the mixture and they'll get oxidized again. So distillation, you stop the oxidation at the aldehyde stage. Reflux, you go all the way to a carboxylic acid. Okay. Yeah, if you're making a hydroxynitrile, you would use HCN. But again, in a real lab, you wouldn't use HCN. You'd probably use potassium cyanide plus some sort of acid to provide the H+. For example, potassium cyanide and hydrochloric acid dilute. But that's just in a real lab. Obviously, in exams, we know nothing about chemistry, just follow the mark scheme. Okay. Hydrolysis is heat under reflux. Yes, that can work. You wouldn't lose a mark for that, but they don't need to specify that. Just say hydrolysis. You can write heat, but most importantly, just include an acid or base catalyst. Okay. Make sense? We can move on. It's the last long response question. Then we move on to these pesky MCQs that people seem to complain a lot about. How do you recommend someone? Well, I recommend, like, the way I did organic chemistry was I just did loads of it. And the more you do it, the more patterns you see. Okay, the more insight you get yourself. Sometimes you realize something and you go like, oh, that's a great way to think about stuff. Like the more you see this, the more comfortable you. Like when I see this, I already know what's going on. Okay, the more you do it, it's just about practice organic chemistry. Okay. Can you explain nitriles and carboxylic acids? You don't need to know the mechanism. You basically just hydrolyze it. So you add water, you add a dilute acid or base, because hydrolysis has to be catalyzed, right? And then you can heat it. And then that gives you COOH. And that happens is because you add 2 water molecules across this nitrile, right? A side product would be ammonia. I don't think you need to know about this. But you can see here, when you add 2 molecules of water across a nitrile, you would add, well, I'm just going to highlight them like this. I'm also going to draw ammonia in this big formula. And this nitrogen atom obviously comes from the nitrogen here that you've lost. So you can see here, the way I've highlighted it is green gives you H2O, and so does purple gives you H2O as well. When you add 2 water molecules across it, that's what happens to a nitrile. You just hydrolyze it into a carboxylic acid. Okay? Does that make sense? Okay, I'm going to assume that makes sense. Some reactions involving 2-bromopropane as shown. State the reagent needed for reaction 1. Well, again, you're just looking at what's changing, right? The whole side chain thing, like this is the side chain, right? It's just a massive distraction. The only thing you care about in organic chemistry is the functional group. So you can see here, you're going from a halogen to this amine. How do you do that? You use ammonia. Okay, you do ammonia and then you do a nucleophilic substitution onto this haloalkane. Okay, it could be SN2 or SN1, doesn't matter. Reagent needed for reaction 1, just ammonia. Okay, straightforward, should be a really simple reaction. State the reagent needed for reaction 2. Oh well, this is like a difficult part because you don't know what X is, right? But let's just see what is going on. So X-3 hydrolysis, we know this is hydrolysis, and you can see hydrolysis forms a carboxylic acid here, right? What do you know about hydrolysis? If you reverse hydrolysis, that could either be a nitrile, couldn't it? Because when you hydrolyze a nitrile, you get a carboxylic acid. That can also be an ester to hydrolyze to a carboxylic acid, but I don't see that making sense because there's not a presence of an alcohol in the side products. This is also removed, so this is removed, and that I assume it's just the excess of that being removed. But right, how do you get from this to hydrolysis. You're seeing me thinking in real time because I actually have to think about this as well. How do you get from... So let me just draw it out. Right. Cleaving an amine. Well, does anyone have any clue what's going on here? I think I figured it out, but I just want to have a look. Isn't it amine? Yeah, it's an amine, isn't it? I'm not tripping. But no, it's crazy. But how do you get from an amine to that? Hydrolyzing an amide. Yes. Is hydrolyzing an amide an A2 reaction, or is it just me? It's A2. Oh dear, that's A2. Okay, for the AS people there, do not worry for now. But this Q is AS. That's confusing. Yeah, I was thinking about hydrolyzing an amide as well, because there's no way you can do a cyanide. I thought of the cyanide, but I now realized you can't do that. But state the reagent needed for reaction 2. Wouldn't that just be any sort of ketone or aldehyde you have? Oh, no, it's not. Oh yeah, I'm stupid. Never mind. So you can see here, I don't know how to explain it to AS people who have never learned this, but you can see here, you have an amine, and you see X. This is removed. So when you hydrolyze X, you have this, right? And you also have this formed. So you're just looking at ways how to recombine these, basically, before hydrolysis. Okay. Oh, wait, you've learned amides in IGCSE, haven't you? You've learned what amides are. So basically, we're trying to figure out how do we, when X is hydrolyzed, when you add a molecule of H2O, you get this, right? So what happens when you reverse it is you take away a molecule of H2O, okay? And the way you do this is you take away the oxygen atom here, the hydrogen atom here, and another hydrogen atom here. So you take away H2O in total, and then you just combine whatever's left, okay? So I'm just gonna go ahead and stick this there. Let me just delete that. Well, if I redraw this to something that's more pretty, I'll just get that. Okay, so how many people don't understand this? Great. Okay. Great. Good. I have to explain this. So can we see here, when X gets hydrolyzed, you form these two products. Okay. This is removed. That just means like we care about this product formed in hydrolysis, but we remove this product. But you can see when X is hydrolyzed, you form both the propanoic acid and this secondary amine. Okay, does that make sense? Does the first bit make sense? When you hydrolyze it, you get two products like this. Okay, so you're thinking, because you need to figure out what X is, because you want to work out what happened from this to X, right? So you need to work out what X is, and to get from the products of hydrolysis back to X, because hydrolysis is adding water, right? We added a water molecule to break X into two molecules, okay? But to reverse the hydrolysis, I just subtract H2O. Okay, I just take away H2O. So it's condensation in a way. So would you know in IGCSE where you have like polyamides, polypeptides and stuff, is where you condense a carboxylic acid with an amine. Okay, and when you hydrolyze that polypeptide, you would get monomers of amino acids, which is just carboxylic acids and amines. So yeah, you just join back the two, and the way you would do this, you can see here. If I just draw out the hydrogen atoms on the amine, you can see like this is a lot of reverse engineering. Working forwards doesn't help in this situation, especially when you're not given the middle step. Okay, working backwards. I love working backwards. I'll just remove the H2O here because it's condensation. Forwards hydrolysis, backwards condensation, right? So I condense these two products together, and then I just join them. I just join them like this. I've drawn it in a weird way, but I've just swapped this out. If I just redraw it, I'll just get this, right? So that is X. That is X. And that makes sense because X, this is X, right? This is X. And when we hydrolyze it, we just add water across it, right? So this is going to gain OH, and this is going to gain H, and that's going to give me this. Make sense? Does it make sense now? Yes. Does anyone still think this doesn't make sense? You. Okay. Let's try to help you then. What part of it doesn't make sense? I assume what happened with like everything. But let me just re-summarize this. Okay, we can't stay here for long, but let me just re-summarize this for you. We have a carboxylic acid, okay, in the products, and we have an amine in the products, right? And this is the product of hydrolysis. So after hydrolysis, I have a carboxylic acid and an amine, right? So what do I have before hydrolysis? Because forwards reaction is hydrolysis, right? Going forwards is hydrolysis, adding water. But going backwards is taking away water, so condensation. So if I condense the products of hydrolysis, I'll get X. If I condense a carboxylic acid and an amine, so these two stuff like things here, I would get the amide, which is a functional group learned in A2. But you can see this is just a condensation reaction to form this product, which is X. Does that make sense? You've learned this in IGCSE, believe it or not, when you learn the amide links. Okay, you get it now. Good, cool. Minimalize sort of like the confusion. I'll also check the mark scheme, mayonnaise, just to make sure. Yeah, propanol chloride. Right. Cool. Yeah, propanol chloride. For the people that are confused, don't be confused. It's A2 stuff. Yeah, it's so obvious, isn't it? Anyways, state a name of a solid catalyst used in reaction 5. Okay, it's another thing where you just don't get this because they're very mean to you, clearly. But yeah, how do you get from an alcohol to this to that? Well, this is kind of like a cycle. They made it like a complete like a recycling bin or something. But you get from this reaction 5, which you don't know what that is, why, and then you do HBr, and then you get this, right? Well, the only reaction you know that involves HBr is electrophilic addition, right? Markovnikov selection, where the halogen ends up on a more substituted carbon. There's a secondary carbon, not the primary carbon, okay? So, well, Y is just going to be propene. Okay, so how do you get from the alcohol to propene using a solid catalyst is what they're asking. Usually you would do this with sulfuric acid as a dehydrating agent, but obviously that's a liquid. What's the solid catalyst you would use for that? It's not elimination of sodium hydroxide because you need a solid. What would the solid be? Yep, for those of you who don't know, it's Al2O3, alumina oxide. But yeah, the oxide works in this case to dehydrate. I do not know why, actually. I've known this before until I looked at the mark scheme like 3 days ago. because I haven't studied the specification. But yeah, apparently alumina works. I cannot explain it, but it dehydrates alcohols. I assume it's one of those reactions where you get like an alumina comb, like sort of a honeycomb shape, and you just sort of pass those propanol gas through it, and then it just dehydrates into the alkene. That's my interpretation. Okay. It's in the syllabus. Because phosphoric acid isn't a solid. Acids aren't solids. You can't use solid acid catalysts because yeah, they can't dissociate into H plus elsewise. Yeah, the question is saying state the name of a solid catalyst. Sorry if I haven't shown the question for longer. But yeah. Pumice. What's a pumice? What's a pumice? I'm searching it up because I haven't heard of that before. Oh, like zeolite, sort of like zeolite, and then with potassium oxide and sodium hydroxide. I would not recommend writing pumice in your answer, although it should be correct because of the mark scheme. Like, a very tired examiner, like a smart examiner would allow that answer. An examiner that's marked like thousands of papers in one day and can't be asked to just look it up, won't allow that answer. So yeah, it's solid. Don't write pumice. Just write aluminium oxide. Why risk it, you know? Why risk it? So just write aluminium oxide. Right. Does anyone have any questions for this question? Especially the amide bit. Again, propanol chloride, not propanoic acid, but yeah. Scambridge things. No questions? We're going to move on to the MCQ as the final bit after. I don't understand the propanoic acid. It will work, matter of fact, it will work. But CIA only allows propanol chlorides. Have you learned about acyl chlorides before? It's basically the same thing. If you look at, this is propanol chloride that I've drawn here. It's kind of like a carboxylic acid, but with Cl at the OH. And then it's the same principle. It's like condensation, but instead of removing H2O, you remove another small molecule, and that's HCl. Okay, HCl, so here. And once you remove that, you get the same product as the one we've drawn with carboxylic acid. It's also the same amide. Okay. So if I highlight it here, just for it to be easier to see. Red is probably not a great color. Okay. It's just a syllabus, I guess, in A2. I didn't do the syllabus, so I didn't know that. But yeah, acyl chlorides are more reactive, so it does make sense that you use it instead of the carboxylic acid. Right? Can we move on? Last chance for any questions before I move on to MCQs. Yeah, they use that mechanism. You don't need to know. Yeah, you do need to know that mechanism actually. A2 mechanism. Sorry. Did we do SN1, SN2? No, we haven't. But we can talk about it at the end of the session if we finish these questions. Okay, I'm just gonna assume there's no other questions because yeah, nobody has any queries. Right. I've included a lot of isomerism here. Okay. But that's just because I've heard a lot of feedback from people. They just really hate isomer questions on MCQs because they take ages. I talked to this guy yesterday. He said if you saw an isomerism question, he would just pick C all the time. Apparently that gives you good luck. Just pick C. But either way, we're not picking C today because we're learning organic chemistry. We're going to try to not pick C. Okay? We're going to try to not pick C. That's our goal. Which compound has the greatest number of stereoisomers? Right, C. No, I'm joking, it's not C. But so the first thing I would do is I would just draw each of them out. Okay, so for A, it's actually not that difficult to draw out because you notice like all of them are hex-2-ene. So really you can use a base structure. So hex-2-ene is going to be like this, right? I'm just going to draw 4 hex-2-enes like that. Oh, the way I draw like skeleton, like that's another way of counting carbons is like one line is 2 carbons, so 2, 4, 6. That's just a way of counting. I think it's faster than counting like what is it, dot to paper, and then like 1, 2, 3, 4. That's like just a faster way of counting. But okay, so you can number them if you want, but I'm just going to number one of them. So this is A, this is A, B, C, D, right? So A, 2 methyl, second carbon, 3 methyl, 4 methyl, 5 methyl. Okay. And now you're counting the number of stereoisomers. Now, let me give you a hack. Okay. Let's call the number of chiral centers, or stereocenters, whatever you call it. Let's call that N. Okay, let's call that N. We're using algebra. You might not know why yet, but this is going to be something different. Hopefully you haven't seen before. So the number of chiral centers is N. Okay, the number of double bonds is M. Okay, and specifically the number of double bonds that can have EZ isomerism or cis trans. Okay, so for example, if I have a double bond like this, where I have 2 methyl groups here and an ethyl group, that wouldn't have EZ isomerism, wouldn't it? Because they're 2 groups on the same side. Okay. However, if I have something like this, where I have, let's say, different groups on each side, there's a hydrogen here, then I would have EZ isomerism. Okay. So I will count that as one double bond. If they don't have EZ isomerism, I won't count it. If they have it, I'll count it. And the whole point of this is I'm going to use the formula. The number of stereoisomers, I just call them stereomers. Iso can't be asked to write 3 more letters, I guess. But the number of stereoisomers is always equals to 2n plus m. Okay? Confusing? All that means is, if I have, let's say, a compound, let's say I have 2 chiral centers, then I'll call n2. Okay? And let's say I have 3 double bonds, but only 2 of them can have EZ isomerism, then I'll just put 2. Then I would have 8 stereoisomers for that compound. Okay, that is quite a useful formula if you don't want to work stuff out. But yeah, that's just a formula that you can use if you want to. That is a hack to every stereoisomer question. It works every time. Very rarely it doesn't work, like number of chiral centers doesn't work, but that's because when you have something called a meso compound where you have a line of symmetry. If you have a line of symmetry in any compound, then it won't be chiral. It just won't be chiral. It won't have stereoisomers. Confusing, but hey, here we are. So let's do this question. You can see here, this double bond we don't count because both sides here we have a methyl group, so we don't count that, right? No EZ isomerism there. Chiral centers, no chiral centers at all, so yeah, 0. There's 0 for A. Let's look at B. B, you can see here, this double bond can have EZ isomerism. You got different groups on each side. Okay, so that's 2 already added to the mix. And chiral centers, there are no chiral centers here. As you can see, no sp3 carbons, no tetrahedral carbons have more than, have 4 groups on them, 4 different groups on them. So that's just going to be 2 squared, 2 to the power of 1, because of this one double bond, 2. Right? C, 4 methyl hex-2-ene. This double bond can have EZ, so that's +2. This is a chiral center with 4 different groups, so that's +2, so that's 4. Okay, it looks like C. Oh, it doesn't look like C. God damn. D, EZ, yes, that's going to be EZ, so +2. This is not a chiral center, okay, because there's 2 methyl groups on this carbon, the same groups, only 3 different groups, so not a chiral center, so 2. That guy was right. Yep, you can guess C every time you do an isomerism question. EZ is in NXL. Oh, EZ just means cis trans. E is cis and Z is trans. Oh, no, hold on. E is trans and Z is cis. The way I remember it is like Z stands for the same side. Like the same side, but with Zs. Get it? The same side. So that's cis. Yeah. I don't know why NXL doesn't teach EZ, but here we go. Any questions on this one? It's simple once I've drawn it out. Or you could have just guessed C and moved on. But yeah. Questions or okay, we can move on. Guess C and move on. Why isn't it D? Why isn't it D? Okay, we look at D, right? This can have EZ. So that's two possible configurations of stereoisomers. But this is not a chiral center because you can see here, this carbon has two methyl groups and they're the same. The two methyl groups are the same. So you won't, it's not a chiral center because you don't have four different groups. Okay, makes sense? Good. Right. This reacts to form alcohol Y in the reaction sequence shown. Well, what is X? You can see here that, well, I'm just going to draw it out. CH3C carbon and a cyanide. So this is a hydrolysis, H plus AQ, so cyanide hydrolysis, right, or nitrile hydrolysis. Then this would form, sorry for the long arrow, this would form the carboxylic acid, this, okay? Just be careful when you're drawing nitriles. Don't forget that this carbon is this carbon, okay? And in this structural formula as well, you have three methyl groups, so 1, 2, 3, and then this spare C is just this carbon here, okay? So just be careful. I think that's the hardest part of the question, unironically. Okay, and then the second reaction, X to Y, is just reduction of the sledgehammer, right? So you would reduce this carboxylic acid into this alcohol. So basically, you just remove this carbonyl group, right? So, name of molecule X. Well, this is molecule X, we know this, right? And, well, the longest chain possible is like this, right? We can number from the functional group, so 1, 2, 3. So you can see on number 2, we have 2 methyl groups. So that's going to be 2,2-dimethyl butanoic acid. Is it butanoic? No, hold on, it's not butanoic. It's 3 carbons. It's propanoic, dimethyl propanoic acid. So it's either C or D. I swear it's C if it's C again. But it's either C or D. And the reason we put numbers behind before the methyl is because in this structure, there's only one possible place for the methyl groups to be. If you put the methyl groups on the end carbon here, the chain would extend and that'll be butanoic acid, okay? And you can't put a methyl group here, obviously. So there's only one place to put the methyl groups. That's why you don't need a number. Class of alcohol Y, next to this alcohol is 1 carbon, so it's primary, that means it's C. What do I know? You can just guess C. Hopefully this is not C. If it is, I'm literally ending the stream. I'm joking, I won't, but okay. Compound X is found in cell walls of some bacteria. Its structural formula is shown. Okay, I don't know. I remember I put this question here because I just thought it would scare a lot of people, and a lot of people just guess C and move on. Hopefully that's not the case. How many stereoisomers are there with this structural formula? What I don't recommend you trying to do is drawing all 17 CH2 units out. Okay, what I do recommend you to do is draw out the bits that I think would confuse you. Okay, for example, this bit is fairly easy to draw out. This bit is not because it's got like more than, like, it's nearly got 40 carbons in it. So what I would do, we know this double bond can have EZ, right? Both sides are not the same. Clearly, this side is not the same from this side. So this is going to EZ, so it's +2 stereoisomers. Like every double bond on chiral center is +2 because of the 2n plus m thing, right? So +2. This side, let's just call this group R. Okay, let's just call it R, and then I'm just going to draw everything here out just to see if there's any chiral centers. Okay, R. So here I can see CHOH. So C, H, and then OH, right? And then that's going to connect to a carbon, which has a hydrogen and a methyl group. And that's going to connect to a carboxylic acid. So you can see here that this is a chiral center. So that's +2. And this is a chiral center, which is +2. So that gives you 6 stereoisomers in total. Let me just make sure. I'm really skeptical of myself. Hold on. So chiral center. Did I miss anything else? I really hope I've missed something else. It doesn't look like it though. Yeah. Great. That's the end of the session. We can end it right there. You can just guess C in all your MCQ you send. Okay. Okay. Add 2 because of the other carbon. What other carbon? Did I miss a carbon? You know what? I really hope I've got this wrong now. Gotten this wrong now. It's D. Oh. Have I missed something? I might have missed something then. Oh, is it because of yeah, I'm devastated after that C incident. But hold on. What did I miss? So carbon there. Oh yeah, oh my god. That's that okay. Okay, yeah, there's 2. Yeah. That's bad by me. After I've literally just taught you the formula. But you can see m equals 1 and n equals 2. So it's 2m, so 1 plus 2, which is 2 cubed, which is 8. Need to pass my maths first, apparently. But I'm actually happy I got this wrong. We can continue the session now because it's not C. But yeah, it's rookie mistake. That's my bad. Unprofessional for me. But yeah. Does that make sense? Or does it not? I mean, I literally got that wrong, so. Okay. Cool. Next one. What are the only structures formed when butanol is heated with concentrated H2SO4? So elimination, clearly, because you can see there's a double bond. So you're going to consider both regioisomers. I mean, what is it called? Positional isomers in the level? Positional isomers and also stereoisomers. So if you draw butanol, you can see that by elimination, that can either give you the double bond on this place, right, between 1 and 2, or this place between 2 and 3. So you can either get this, or you can get this, right? And of course, this is cis. I mean, this is trans, not cis. What am I doing? This is trans, so you can also have the cis isomer, right? So now you just got to look at the options. It's going to give 3, not 2, because of the stereoisomerism. But yeah. The answer should be, this is the same as that. This is not right because that's isopropyl. That's the 3 carbon chain, not a 4 carbon chain, so that's not right. So so this is trans, right? This is trans because the CH3 on different sides. This is cis, and this is but1ene. So yeah, it's B. Make sense? Did I do it too fast? I feel like I've done it a bit too fast. Does anyone not get that? You don't get it. Okay. Can we repeat this? Yes, we can repeat this. Okay. Let me just put it to the side. It's getting a bit messy now. So butane 2-ol, we draw butane 2 out like this, right? When you heat it with concentrated H2SO4, it's going to be elimination. So 2 ways to eliminate is 1, you eliminate on this side with the alkene and kick this alkyl group out, right? The second way to eliminate is this side and kick this alkyl group out. So you either get but1ene or but2ene, but of course you can have cis or trans but2ene. But1ene, you won't have cis or trans because, well, you have 2 hydrogens on one side, so no cis trans there, but definitely cis trans for but2ene. So you can see here, this is the cis but2ene, this is the trans but2ene, and this is but1ene, just drawn in like an upside down manner. So it's B. Does that make sense now? Cool. Great. Okay. Beta carotene, another molecule that is just massive, and most people will put C here. Beta carotene is responsible for the orange color of carrots. Beta carotene is oxidized by hot concentrated acidified KMNO4. When an individual molecule, okay, it's just asking you, how many product molecules when you do these this oxidative cleavage reaction, how many product molecules contain a ketone functional group? Okay, so basically, you just got to break them off one by one and figure out which one gives you a ketone. Unfortunately, but the easy way to figure this out is we can use like a kind of like a schema first. Let's say I have butene. You know, when I break this off, I'm gonna get 2 aldehydes, right? You can see I will get 2 aldehydes, and those are going to get oxidized further to carboxylic acids. Okay, what I cannot do I cannot oxidize them into carboxylic acids if I have a methyl group here. When I break this off, this is going to give me a ketone, right? So you can see an alkene that is tri-substituted in a sense that it has all 3 groups surrounding the carbon will form a ketone. Okay, and basically just trying to calculate that. So we can see here, when you break this off, right, that's going to give you a ketone. That's going to give you a ketone. And that's not going to oxidize further because you can see here, this alkene here is tri-substituted. If you look at this carbon, it's got 3 carbons next to it. If you look at this carbon, it's got 3 carbons next to it. So this alone is going to give you 2 ketones by breaking this off. Okay. If you look at this double bond, for example, you can see breaking this off will give you 2 aldehydes. This carbon, for example, is only di-substituted by 2 carbons. When you break this off, it won't give you a ketone. It will just give you an oxygen atom here and then hydrogen atom here. That's an aldehyde, okay, not a ketone. But this here is tri-substituted. Break it off, it'll give you a ketone. This side, however, on the right, so the left side will give you a ketone, the right side won't give you a ketone because it's only di-substituted. You can see only 2 groups. So this is 2 ketones, this is 1 ketone, and anything basically with a methyl group next to it will give you a ketone. Does that make sense? Just following that logic, or does it not make sense? You don't get the question. I think I explained it using fancy terms, but like, you just gotta imagine, right? When you break open this double bond, it might be easier with like an actual pen and paper, but when you break open this double bond, you replace it with an oxygen on each side, right? So if I kind of draw this out, just that part of the molecule, you can see I have an alkene here, right? I have an alkene here. When I break it off, I can almost kind of rub out the middle and then just add an oxygen to it. Can you see that? And can you see that this is a ketone? And so is this. This is also a ketone. And you're being asked to count the number of ketones, basically. So you just got to imagine what is a ketone and what isn't. So you can add oxygen atoms here, sort of, just cut them off. So this would give you 2 ketones, as I've demonstrated. This would give you a ketone because you add an oxygen here. You can see that's a ketone, right? That's 1 ketone. This side wouldn't be a ketone because there's only 1 carbon here, right? This side would be an oxygen, a hydrogen, I mean. So that's an aldehyde / carboxylic acid when it gets oxidized. This would also give you a ketone, you can see here. This would give you a ketone, you can see here. This would give you a ketone, you can see here. And finally, if you split this up, that will give you a ketone, right? And this would also give you a ketone. So that's +2. So if you count 2 + 2 is 4, and then just 8. 8, hold on, did I miss something? That means I missed something because in the MCQ. How many of these product molecules contain a ketone functional group? Oh, does it mean like individual product molecules? Wait, 1, 2, 3, 4, 5. Oh, this is embarrassing. Hold on, you split it up. 2, 1, 1, 1. Have I miscounted anything? Is it asking me to count the number of ketone functional groups, or it's asking me to count the product molecules? Oh, they want molecules. Okay, they want molecules, not groups. My bad. Okay, so yeah, when it's cyclic, you would break it up like this, but that's one molecule. That's 2 ketone groups in one molecule. That makes a lot more sense. So it's 2 ketone groups in one molecule. But you can see here, if you split this double bond, or you can split this one as well, this part of the molecule will get like detached out of that. You can split this double bond as well, and then that gets detached as well. But when you split the double bond inside the ring, you would get 2 ketone groups like this, as you can see here. I've drawn it kind of cramped. Let me just make it bigger. But you get 2 ketone molecules like that, but that's only, functional groups, but only in one molecule. Can you kind of see that better now? That's not an iodine, that's just a 1. Okay. Yeah, it is B, because this would be counted 1. This would be counted as 1 molecule. And then these 4 cuts would be counted as 1 each. And this would also be counted as 1. So it's B. Does it make sense? Someone said, wait, what? Does it not make sense? I know it doesn't make sense, to be fair. It's quite difficult to explain. But how do I do this? So, right, let's look at this double bond in particular, right? You know it's going to cut all the double bonds open. So when I cut this open, right, this part of the molecule and this part of the molecule, whatever's on the right, is going to be separated. Okay, it's going to be separated. Does that make sense? That's the first step to understanding it. When you cut the double bond here, because it's going to oxidize that double bond as well, the two molecules are going to be separated. Okay, so this is going to become an aldehyde, and so is this, but they're going to be detached from each other, right? Just cut right there. Okay, but then if you cut this bond now, right? If you cut this bond and add an oxygen next to it, these two are going to become ketones, right? Ketones like that. But that's still one molecule because it's connected in a ring. It's connected in a ring. So actually, you have 2 ketone functional groups formed, but you have 1 molecule only. So you count that as 1. The ring doesn't break. The ring does break. It does break because you cut it open, but the molecule is whole. Like it's a whole molecule by its own. Okay. Yeah. Unfortunately, we would have to move on because it's 2:54 in my time, and we have to finish this as much as we can. Yeah. Okay. So a bit of a speed run. What is produced when X is heated with NaOH? Okay. By the time of this, by like the whole, is the entire structure one monomer? What do you mean one monomer? It's not a monomer, it's a molecule. Okay. It's the orange pigment you find in carrots. That's where they get it from. But anyways, what is produced when X is heated with NaOH? I've done this so many times today, so you should be able to do it too. Is basically when you see an ester, you just cut it open. Okay, you just cut it open. So just to be clear how to cut it open, I'll just number them. So this, I'm going to number this 1, 2, 3, and 4, 5. So you can see I'm just going to draw a 5-carbon chain. I'm going to call this 1. Carbon number 1, I have a carbonyl group. So here, you can see that this bears the oxygen as well. So that's going to be OH, right? OH. And then on carbon number 4, I would have this alcohol group. Because it's hydrolysis, right? NaOH AQ is hydrolysis of an ester. On carbon number 4, I'm bonded to another oxygen given by the water. Okay. Now, the only difficult part about this question is why do we have ONA here? Well, that's because in basic hydrolysis, right, in alkaline hydrolysis, you can know that the carboxylic acid, obviously, is called an acid. And when you have alkaline conditions, that's going to get deprotonated, right? So OH is going to go ahead and grab this proton, okay? You can just remove that proton. I'm not going to draw the mechanism in full, but what's going to happen is this oxygen becomes negative and then sodium goes on and complexes with it. Okay, so the correct answer would be C, because they're just drawn it in a different way, but really 1, 2, 3, 4. On the 4th carbon, we have an alcohol, and the 1st carbon, we have this carboxylate anion here. C? Well, yeah, joke's old now, isn't it? Every dog has its day. Okay, does that make sense? Why does the OH bond to carbon 4? Why is the OH bond? Well, because you're adding water across it, right? So you're splitting this bond apart, and then you can kind of draw it out ugly like this. So you can draw it out. You know this bond is going to be disconnected. So we added H here because it's a carboxylic acid, and the only way to do an esterification is adding an OH here. Okay, so when you do esterification, you remove H2O like this, and you just reform the bond. Does that make more sense? You just got to number the carbons and figure out, like, be careful on what is going where. Why doesn't OH become ONA? Because alcohols are significantly less acidic than carboxylic acids. Okay. It's actually unstable for an alcohol to be deprotonated. Carboxylic acids, however, are much more acidic. Okay. We got to move on. We don't have much time left. I almost read that as autism for some reason, but artemisinin is a powerful anti-malarial drug. Didn't know that. How many chiral centers are in each molecule of artemisinin? Okay, well, this is like another big scary molecule, but really it's an easy question. So when you see questions like these asking about chiral centers, whatever has more like 4 groups on it is a chiral center. Okay, that's it. That's pretty much it. And what I mean by that is it might help if you draw in all the hydrogens. It genuinely might help. Okay, for example, if I look at this carbon here, right, you might not think that's a chiral center, but really there's a hydrogen here because the carbon needs 4 bonds. So that is a chiral center, right? This carbon has a hydrogen in it, so that's a chiral center. This has a hydrogen in it, that's a chiral center. This also has a hydrogen in it, that's a chiral center. This is obviously a chiral center, doesn't have a hydrogen on it though. It's already got 4 bonds, right? This is a chiral center with a hydrogen, and this is also a chiral center. Don't miss that out. Okay, so 1, 2, 3, 4, 5, 6, 7. Did I miss anything? Just making sure. 1, 2, 3, 4, 5, 6, 7. Yeah. Does this make sense? Does counting chiral centers intimidate people? How would the formula work here? What do you mean by how would the formula? Isn't the C attached to 2 oxygen? Which C? There's a lot of C's in this. Can I explain counting? Okay, I'll just explain this again. It's quite quick. But basically, anything that has 4 groups on it is going to be chiral because it has 4 different groups on it. And you can see like there's not really a plane of symmetry in this molecule. So you don't really need to worry about that because as I said before, if you have a plane of symmetry in a molecule, chiral centers become more complicated. But in this case, you don't have a symmetry plane. So really, you're just looking for carbons that have 4 groups on it. For example, this is a chiral center. That's quite obvious, right? This is a chiral center because you have a hydrogen on it, and that's 4 different groups. Like, it's going to be different if you go this way and if you go this way, okay? Because this leads to different routes. This way, it leads to different routes as well. That's why it's different. So this is a chiral center. Don't forget about the implicit hydrogens, really. So if you see somewhat like a chicken leg shape, like we call these chicken leg hydrogens, like because they're hard to kind of spot. But if you see this chicken leg shape, then it's going to be a chiral center. Okay, you can see this chicken leg shape. That's a chiral center. This is also a chiral center, right? And this is already a chiral center. So yeah, you can see like something like this wouldn't be a chiral center because it has 2 hydrogens on it, right? So it won't be 4 different groups. So therefore not chiral. So 1, 2, 3, 4, 5, 6, 7 is just C. Okay, and of course an sp2 carbon with the carbonyl would be planar and not chiral. Make sense? Hi, am I late? No, we've just started. You're 10 minutes early, actually. Okay, we can move on. Okay, there's no questions here, right? I've explained it twice. Okay, cool. Right, what is this question? Heating compound X. Okay, it's retrosynthesis again. Retrosynthesis just means going backwards. Oh, hold on, someone's got a question. How is the C with the 2O a chiral center? Like, as in, are you talking about this carbon? Is that what you're talking about? The right one. Oh, this one. That one. How is that a chiral center? Well, you gotta not look at it like as the immediate groups, right? Because if you look at it immediately, the next thing you have is just an oxygen. Or you think, oh, that's 2 same groups. But really, you gotta follow the whole path, right? So if I follow down the route, you can see that leads to a methyl group. But if I follow down this side, that's gonna lead to an ester group. It's different. Just because they're the same atom doesn't mean they're the same. Okay, you just gotta like go all the way, and you can see like you can really go all the way to distinguish it. Like you can go down this way and then go down the methyl and go down like the whole molecule. But either way, having the same atom doesn't mean it's the same thing. Okay, so again, C. Unfortunately, C. Heating compound X that under reflux with an excess of reflux with excess of acidified potassium dichromate. So you know that's from an alcohol to a carboxylic acid, right? Heating in reflux using that oxidizing agent produces a compound Y. So you know there's going to be an alcohol here somewhere. Compound Y produces hydrogen gas with sodium metal. If you don't know what that is, it's an IGCSE reaction where you react, for example, a carboxylic acid with like a sodium metal. And then I'm drawing it skeletal formula, but I really don't need to. And then you just form this. Right, again, it's like a deprotonating reaction plus H2. That's why you get the hydrogen gas. It's just the hydrogen and the sodium swapping places, okay? And forms orange crystals with 2,4-DNPH. That's a ketone aldehyde test, okay? So if there's a ketone or aldehyde in compound Y, it's going to form orange crystals. You just have to know that, okay? So we know in compound Y, we can label, there's going to be some sort of acid or alcohol. This also works with alcohols, by the way, so OH/acid. Well, it makes more sense to have an acid in compound Y, doesn't it? Because we've just said heating compound X under reflux of this gives me a carboxylic acid in compound Y, right? So I'm just going to say compound Y has carboxylic acid. And it also has a ketone or aldehyde because it forms orange crystals with this. Okay, so I can also write ketone or aldehyde. And now I have all this information, I'm just going to work out what X is. Okay, what you can also do, the second method of doing this is basically just picking a compound, trial and error, and just go down the route. Okay, for example, if I pick A here, if I react it with acidified potassium dichromate, it's going to oxidize this alcohol to a ketone, right? Don't forget that secondary alcohol is going to be oxidized as well. So if I go down this way, then I'll oxidize this to a ketone, right? And this is going to become a carboxylic acid. That matches the description that I've written down that it's going to have an acid and aldehyde or ketone, right? So just to confirm, when it reacts with sodium, this hydrogen would be released and you would get hydrogen gas. And this ketone will react with 2,4-DNPH. You don't need to know why, to form the orange crystal. Okay, so A is the answer, but of course you can do it for B. For example, if I did B, then I would have two ketones, first of all, oxidized, right, from X with potassium dichromate. And that wouldn't produce hydrogen gas because you didn't have an acid or an alcohol to do that. Okay, we can try with C as well. C, there's a tertiary alcohol. Tertiary alcohols can't be oxidized. So we can just ignore that. But this bit is going to get oxidized to an acid. You would produce hydrogen gas because of the acid, but you don't have a ketone or aldehyde to get the orange crystals, right? And B would be just using the same logic. So A is the correct answer here. Does that make sense? Someone said it's confused. They're confused. So, confused. Okay, confused. So you know compound Y. If you produce hydrogen gas with sodium metal, you need to have a carboxylic acid, right? And you need to have an aldehyde or ketone to form the orange crystals with 2,4-DNPH. Make sense? And it's asking what X is, not what Y is. Okay, so X is getting oxidized with reflux and excess of potassium dichromate. Okay, so I'll just assume that, let's just say X is A, okay? Answer A here. Then when I oxidize it, I'll get a ketone from the secondary alcohol and a carboxylic acid from this primary alcohol because it's heating under reflux, so I'll get a carboxylic acid, not an aldehyde. And when I react with sodium, I'll get hydrogen gas because of this acid group for this reason here, and I would get orange crystals because of this ketone here that reacts with the DNPH. Make sense? I'm just waiting for the other person to type. How does CH2OH become a carboxylic acid? Well, we can draw out CH2OH, can't we? So I have this thing here, and let me just draw out CH2OH. It's just this. And when you oxidize it, you just add a carbonyl group like that. Does that make sense now? You just oxidize it with reflux potassium dichromate. Okay, cool. Okay, we're 8 minutes over time, but 3 questions left, is it? We can all guess C. No, I'm joking. Structural isomerism and stereoisomerism. Okay, yeah, context. How many isomeric compounds with the molecular formula this contain 2 CO, so 2 carboxylic acid groups, and 1 CC double bond? Right, so the good thing about this is carboxylic acid groups can only be at the end of the molecule, but the bad thing about it is you also have to consider branches. Okay, so for example, the simplest, I mean, the way I would do this is do it systematically, obviously, but just draw out as much things as you can. Can I draw out CH2OH? Like in displayed formula. CH2OH would just be this. That's what it means. Okay, so anyways, as I was saying, I would just like draw out as much things as I can, but also, of course, do it systematically. So it's going to be 5 carbons from the molecular formula, I can tell. And the first thing I can think of is this, right? That's 1,5 pentadioic acid. So you're gonna add a double bond. You need a double bond, right? Double bond, you know, it can't be here because this carbon would then have 5 bonds. It can't be here, so it has to be between here and here. And if when you put it here, that's going to be the same as if you put it here because that's symmetrical, right? Or the other way to think about it is 1, 2. That's a 2 alkene. That's also 1, 2. That's also a 2 alkene. Okay, so this can either be E or Z. Notice how it can be E or Z because of the hydrogen here. That's different groups. So you know that's 2 possibilities already, right? And then the other possibility we have to consider is branches. So always start with the carbon skeleton. When you see stuff like this, always draw the carbon skeleton first. Okay, so for this, I'm going to draw out a 4 carbon skeleton. I'm just going to like go down the number of carbons really. So 4 carbon skeleton, the first thing I can think of is this and this. Okay, and the double bond, it's possible to have it here or here, right? That would have EZ because of the 2 groups on this side being different, and there's a hydrogen here, so 2 groups on here different as well. So that's EZ, right? But so that I'm just gonna label EZ. But the other possibility that I've considered, this would not have EZ because of the 2 same hydrogen groups on this side. Okay, so that's only 1 isomer, right? So that's a 4 carbon chain gone. We can go down to 3 now. So let's just try 3 like this, right? So, well, that's the same as the 4 carbon chain, really. But what you can also have here is if you put the carboxylic acid group here. So let me just draw out this. If I put it here, like really, you just got to do trial and error. I mean, not trial and error, but like you just got to consider what the possibilities are. You can see you can't put it here because of the 5 bond reason. You can't put it here either for the same reasons, but you can definitely put a double bond here or here. Okay, so if you put a double bond here, that wouldn't be EZ because these 2 sides are the same. Yep, they're the same. And you can, that's one way to do it. And the other way to do it is just putting a double bond in that position. Okay, so if you count now, like if you look at this now, if you look at my working now and you haven't followed through, you would have no clue what I was doing. But now if you count, that makes sense. Okay, so that's 2. This is 2. This is 1. This is 1. This is 1. So 7. Okay, it's C. Right. Let me just look at people's questions. How many combinations do you draw? How do you know? You can see like the basis of doing these questions. These are like really tricky, like troublesome really. But I start with a 5 carbon chain because there's 5 carbons, right? The second thing I did is decrease it to a 4 carbon chain. And the only way to put the 5th carbon is like this, right? It doesn't matter where you draw because it's the same thing. And then I decreased to a 3 carbon chain, so like this. The only way to put it is like this. Which is the same as this, I realized. So I stopped, and these are like the 2 carbon structures only. Only the 2 carbon structures possible here. But then there's like loads of ways you can put the carboxylic acid groups, right? So I just started putting the carboxylic acid groups. For example, there's only one way to put it here, but for on here you can put it like, for example, like this or like this. Right, and then you just add the alkene in and then figure out EZ as well. You just gotta like add them up bit by bit. That's how you do it. Okay. Does that make sense now? Does that make more sense? You just gotta like try it out. And it would be really lengthy if I just went on and go like, oh, that's why you do this, that's why you do that, because it's 7 combinations. So yeah, you just gotta really practice and work them out yourself. And of course, if you have anything, I'll help you after the session. Right. 2 more and we're done. Which pair includes a hydrocarbon without a chiral center? I've included this question because it's a lot of information, it looks like. But I've also included this question because it's extremely easy. Okay. You remember when I said when something has a line of symmetry, it really won't be chiral. Okay. So you're looking for a pair of hydrocarbon without a chiral center. So basically you're looking for a line of symmetry. Right? So without a chiral center. You can see in A, option A, this is definitely chiral. I can't see a line of symmetry anywhere. If I could draw now if I wanted to. So you can see it's like this. This is definitely a chiral center with 4 different groups, right? This, you can see, has a line of symmetry. Can you see that? On this carbon, you have this group, and that's the same. So I can even draw it out if you want. So we start with this carbon, right? And then on that side, I would have this, and on that side I would have this. And that's, hold on, I need to draw this from the left to right. CH3. Oh yeah, hold on. My brain is just not working at this point. Oh, you have to draw them out. I guess trick doesn't work. You have to draw them out for this one. But yeah, that is chiral as well. I mean, I would just draw them out, really. But sometimes it's obvious when it's not a chiral center. Sometimes it's really obvious. I'm trying to find an example for that. For example, like you see this carbon, right? You see this carbon. On that carbon, you have this group and this group attached to it, right? And you have this and this as well. So you can see you have 2 methyl groups on the same carbon. Remember the brackets always go to the carbon in front. I think I just forgot that as well. So you can see specifically on this carbon, you have 2 methyl groups attached to it because this bracket belongs to this carbon and this methyl group belongs to this carbon as well. So that's not chiral, right? Because you have 2 methyl groups on the same carbon. For this one, we can look at that as well. Yeah, that's not chiral as well because you can see CH3 That means on the final carbon, we have 2 methyl groups on it. That's literally like the same kind of reason why it won't be chiral. So the answer is D, but for the sake of proof by exhaustion, I'll just do C and B as well. So C, well, you can draw it out. I just recommend drawing it out at this point. That's a chiral center, right? This, well, you can see that this is not a chiral center, but this is a chiral center. Okay, B would be for the same reasons as well. Does anyone need me to go through that again? My brain is just fried at this point, so. If you think inorganic or physical is better, um, you're a fudge stick. Okay, we can move on. 3-methyl hexanthreol, again another isomerism question, reacts with hot concentrated sulfuric acid to form several isomeric compounds. So again, if you see hot concentrated sulfuric acid, you know that's elimination, right? So you just got to look for ways to eliminate. The double bond is always going to be next to the carbon that's bearing the alcohol before. So the first way I can think of is putting the double bond here, right? So let me just draw that out. And that can have EZ isomerism, okay? There's 2 different groups on different sides. So that's 2 on its own. The second way I can think of is putting the double bond here, right? So like this. That cannot have EZ because there's 2 hydrogens on the same side, right? So that's only 1. And then for the third one, you would have the double bond here. So like this, okay? And in that case, you would get 2 as well because this can have EZ. You have different groups on each side, right? So that the answer would be 2 plus 2 plus 1, which is 5. Is that too quick as well, or do you need me to go through that? It's C. Oh my, to be fair, like, why is it always C? How many questions did we have that were C? So we had, oh my God, that's a lot of annotation I've done today. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 questions. How many of them are C? 1, 2, 3, 4. Wait, hold on. I can't even count at this point. 1, 2, 3, 4, 5. 5 questions. That's not that much, to be fair. It's only like half. Yeah. Okay. Right. Well, that's it. That's the last question, which I'm kind of glad actually. I'm gonna send it as a PDF over. I'm gonna save it and then I don't even know if these notes are worth looking at, to be fair, because it's quite difficult to interpret what's going on with my annotations. But does anyone have any key questions? Just like literally any inquiry about organic chemistry. Not limited to this, obviously. Will there be a physical chemistry session? Mm, probably not, unfortunately. I think I'm quite bad at physical chemistry compared to organic, believe it or not. You don't get cis-trans. Do you want me to explain cis-trans? We've done quite a lot of cis-trans today. How much should you practice? Obviously, the more the better. So cis-trans, you know what? I'll just send you a video that I think is good. I think you'll explain it better than me. Like it's one of those things like you have to learn it first, and then once you don't get it, you go back to someone else and ask. You have to know what's actually going on first.